AI has become mega popular these days. Let's look at the inner workings of neural network and the current state of the art. AI, artificial intelligence, is a term was coined back in 1956. In 1958, Cornell University psychologist Frank Rosenblatt built the perceptron based on the design to mimic how neurons fire in our brains. So here is a basic model of how neuron in our brain works. An individual neuron can either fire or not, so its level of activation can be represented as a 1 or a 0. The input to one neuron is the output from a bunch of other neurons. But the strength of these connections between neurons varies, so each one can be given a different weight. Some connections are excitatory, so that they have a positive weights, while others are inhibitory, so they have a negative weights. And the way to figure out whether a particular neuron fires is to take the activation of each input neuron and multiply by its weight. And then add all this all together. If there is a sum is greater than some number called bias, then the neuron it fires. If it's less than that, then the neuron doesn't fires. Rosenblatt's perceptron had 400 photocells arranged in a square grid to capture a 20 by 20 pixel image. You can think of each pixel as an input neuron with its activation being the brightness of the pixel. Although strictly speaking, the activation should be either 0 or 1, we can let it take any value between 0 and 1. All of these neurons are connected to a single output neuron, each via its own adjustable weight. So to see if the output neuron will fire, you multiply the activation of each neuron by its weight and add them together. This is essentially a vector dot product. If the answer is larger than the bias, the neuron fires. And if not, the neuron doesn't fire. Now the goal of the perceptron was to reliably distinguish between two images, like a rectangle and a circle. For example, the output neuron could always fire when presented with a circle, but never when presented with a rectangle. To achieve this, the perceptron had to be trained, that is shown in a series of different circles and rectangles, and have its weights adjusted. Accordingly, we can visualize the weights as an image since there is a unique weight for each pixel of the image. Initially, Rosenblatt set all the weights to 0. If the perceptron's output is correct, for example, here it's shown as a rectangle, and the output neuron doesn't fire, no changes made to the weights. But if it's wrong, then the weights are adjusted. The algorithm for updating the weights is remarkably simple. Here, the output neuron didn't fire when it was supposed to because it was shown a circle. So to modify the weights, you simply add the input activations to the weights. If the output neuron fires when it shouldn't, like here when shown a rectangle, well, then you subtract the input activations from the weights. Then you keep doing this until the perceptron correctly identifies all the training images. It was shown that this algorithm will always converge so long as it's possible to map the two categories into distinct groups. The evolution of human intelligence is through the accumulation of data over many thousands of years. By the mid 2000s, most AI researchers were focused on algorithms, but one researcher, Fifi Lee, thought maybe this artificial neural networks needed more data to train on. So she created ImageNet, the database of 1.2 million human labeled images, which at that time was the largest labeled image data set ever constructed. Competing in this competition would have an outer layer of 1,000 neurons, each corresponding to a category of object that could appear in an image. If the image contains, say, a German Shepherd, then the output neuron corresponding to German Shepherd should have highest neuron activations. Do not include the correct category. This is so-called the top 5 error rate. In 2010, the best performer had a top 5 error rate of 28.2%, meaning that nearly a third of the time the correct answer was not among its top 5 guesses. In 2011, the error rate of the best performer was 20.58%, a substantial improvement. But the next year, an artificial neural network from the University of Toronto called AlexNet blew away the competition with a top 5 error rate of just 16.4%. What set AlexNet apart from other networks was just a size and a depth. The network consisted of 8 layers and in total 500,000 neurons. To train AlexNet, 60 million weights and bias carefully adjusted using the training database. Because of all the big matrix multiplication, processing a single image required 700 million individual math operations. Team managed by pioneering the use of GPUs, graphical processing units, which are traditionally used for driving displays and screens, but reused for past parallel computations. The Alexandria paper describing their research has now been cited over 100,000 times. The neural network takes a lot of computation to train and run the network, but the improvement in performance is worth it. With others following their lead, the top 5 error rate on the ImageNet competition plummeted in the years that followed, down to 3.6% in 2015. That is better than the human performance. Papers with Code is a community-driven platform for learning about the state-of-the-art research papers on machine learning. It contains from a computer vision, NLP, knowledge base, and so on. If you search for an ImageNet classification with the deep CNN models, you can find the paper as well as the code. You can try with the code. Right? You can also search for image classification. You can find the state of the art, and we can find the accuracy and the error rate of the current state of the art. Thanks for
Thank you
watching.
for watching
Please
Did You
share
Know
and subscribe.
Semiconductors channel.
Once again,
Thank you.
thank you.